So are we ready? Yeah. Okay. I think I'll get started, yeah? Okay, folks, thank you for your patience with that. I hope you get your royalty. Today is, I think, a really important topic. I almost regret that it's happening so late in the term. I think it's one of the standing big challenges for everything we've talked about this term is how to deal with more interesting sensor basically models. So output feedback, you might, if you're in RL, you might be calling this pixels to torques, for instance. This is sort of the generalization of everything we've been talking about, where we used to be thinking about full state feedback. Now we're going to talk about output feedback. Okay, so far in class, we've had models of the form f of xn, un. We started adding in disturbances, wn. And we've had controllers that were of the form un pi of xn, right? And we spent a lot of time thinking about different ways to come up with the functions pi that mapped our states to our actions. What we're going to do today is generalize this, right? We're going to be thinking about now systems that have their outputs. With another set of equations here. In state space form, it tends to look like this. Vn is going to be another random input. We tend to call it V instead of W just to distinguish this is our sort of process noise. And this is now our measurement noise. Okay, but it's just another random input. And we have some y's, some observations that are a function of our state, our control, and this randomness. And really, this is a more holistic view of what the control problem is, where now I really should be thinking about the system I'm trying to control, which we've stuck with tradition and called the plant, right, as a system that takes some series of u's in and produces some series of y's out. And in some sense, the fact that inside it has some internal state variable x is almost inconsequential for using the system, right? All we really have access directly to is u and y. Okay. And the task today, then, is to generalize this state feedback to something that is an output feedback that's using y. And there's a lot of ways you could think about doing that, right? So maybe the first obvious thing you might try to do, maybe I want to say u of n is just pi of yn. Okay? I just take my observations and use them directly as a function. We'd call that static output feedback. But there's many other choices that we'll sort of go through today. Another one you could imagine, which is very common, is that I could try to build some state estimator and try to estimate the state, the internal state x, and then use my same original feedback controllers, state feedback controllers. And I would generally call this observer-based feedback. Observer is kind of synonymous with state estimator. Okay? And there's a huge wealth of control ideas that are sort of connected to that approach. But there are more options too, and I want to make sure we explore the richer space of output feedback control. Okay, so for instance, if we just to think about the implications here, just to think about why did we do this in the first place? Like, why did we choose u as just some function of x? Really, there's what information does the controller have available to it at time n, right? So maybe the robot woke up at time 0. Okay, it started taking actions and observing states from time 0 up to time n. So hypothetically, you could use all of the information of all the actions you've taken and all the states you've observed up until time n to make your decision, right? And obviously, the optimal actor, the optimal policy, could not do more than using all of the available information. Okay, so the reason that this is okay and the reason that this is clearly optimal is that xn, when I've written my dynamics like this, is that if I know xn, that's a sufficient statistic for the entire history. It doesn't matter what the previous x's were, what the previous u's were. If I know x, then I know everything that I need to know to predict the future. Nothing else matters. X perfectly summarizes the past. Okay, so take that observation and now try to generalize that to the output case. Okay, if I have now a history of y's and a history of u's, I mean, you could imagine taking a controller that's saying, and certainly the optimal controller must live in the set of controllers that, for instance, takes the previous observation, the previous action, but the entire history of observations all the way back to 0. Right? So I could write a controller that tried to use that entire history in order to make decisions. And certainly, like I said, the optimal controller must, it can't do better than something that knows all that information. But that's a kind of a nasty space of controllers to live in because like the number of inputs grows every time step. For finite horizons, actually, this is not crazy. People do that. Okay? And there's ways that if you do this, the problem can be convex, even though the whole problem in infinite horizon would not be convex, for instance. Okay, but that's sort of a basic idea of sort of where we're coming from, is that what we're missing if we don't know x is we don't necessarily have just a single vector that can be a sufficient statistic of the entire past. Right? So if you do want a sufficient statistic of that, you can write it like if you know the probability distribution over xn conditioned on all of these things, all the way back, then this is actually the same sort of, if you have a distribution over x's given all that information, that is the sufficient statistic for that it will summarize the past. Sometimes this has a nice efficient representation that doesn't require the entire, that you can somehow write a recursive form for this. Okay? But in general, you need the entire belief distribution. This would be called a belief distribution. Over x's, given everything you've seen before. Okay, and in the full glory, we've seen distributions on the van der Pol oscillator do cool things. We've seen distributions of the rimless wheel do cool things. These distributions can be very rich for nonlinear systems, okay? They are not necessarily efficiently representable, especially in high dimensions. So representing the belief distribution with a finite set of numbers can be a challenge. But if you could represent the belief distribution, then certainly we could try to write controllers that took our representation of belief and tried to take the optimal action. And that's more standard fare for partially observable Markov decision processes. In discrete time, discrete state, discrete action, it's more tractable. It's still bad, actually. Okay, but in its full glory, it's a very hard problem. Does that make sense, that basic idea? We're missing the state estimate as an efficient summary, so we're in a much harder world of trying to come up with approximate summaries or representations of that distribution. There are more options, though, and things that you've probably seen if you've been dabbling with RL or other, control-related ideas. It's pretty common to say, let's take a history of observations and actions, but we'll just take a short history of observations and a fixed number of observations and actions, right? So what if I made policies that were out of yn minus 1, un minus 1, but I'll truncate it. Call that the truncated history of observations and everything. This can be an extremely effective class of controllers to try to search over, but it should be seen as an approximation of the full history. Some systems can be the optimal policy can be perfectly represented with a finite history, some cannot. We'll try to understand that a little bit. Okay, so that's kind of if you had, for instance, a neural network policy that took in the last few observations, right, then that would be in this class. These days, you'll see things like this too, right? Right, where z is some latent vector, maybe some sort of the output of some learned state representation, let's say. Now, when you're working with learned state representations, some possibly not human interpretable vector z that comes out of let's say, a neural network, still that has to come from somewhere. So oftentimes you'll see something like the encoder for that be another neural network, which takes, for instance, a truncated history okay, this could be my latent encoder, if you will. Could be a neural network or something like this. But that in some sense is another way to live in this space. It's a particular parameterization of living in this sort of space of controllers. You might see, instead of this, you might see the encoder having dynamics of its own, right? It could be it's always a choice of how you choose the ends in these output feedback problems, okay? But let's just keep it like that. That's okay, right? So this would be sort of a state space model for that latent vector. Maybe a recurrent network would look like this. Maybe a feed-forward network would look like this, okay? But those still come from somewhere, okay? This, again, the way you should think about these when you see this kind of representation is really that z of n if the learned state representation is doing a good job and you're trying to be a good representation for decision making, then you should be thinking about that latent vector as playing the role of an approximate belief distribution. Right? It has to somehow capture enough about what's happening in the state in order to make the right decision. So that's kind of the space of possible output feedback controllers that we can search over. And the big thing that sort of happened here, especially, I mean, really, in almost all of these, what happened is I've had to grow my notion of what a controller is from, it used to be an input-output function that took states in and took actions out. Now all of these are different ways to parameterize a controller as a dynamical system by itself, okay? So now what we really want to think about is the controller is itself a dynamical system. It's taking observations in, it's spitting out the controls, and it too can have an internal state. I'll call it X controller of N. So this is another dynamical system. If it's represented in state space form and using latent vectors, then XC could be my Z. XC could be my history of observations. XC could be my state estimate in my observer. Okay, but all of these are just different approximations, or different ways to describe the dynamical system that is our controller. Okay, so the big thing is if I don't necessarily have everything I need in a single Y, then optimal control switches from just being an instantaneous function, U, to being an entire dynamical system. So the problem of doing output feedback design is trying to design now the controllers that take this richer form, that have potentially their own dynamics. Okay, so with that kind of as a setup, is that clear? Anybody have questions at that level? People feel like they've seen this a bunch nowadays? Yes, no? How many people have seen belief space planning kind of things in POM-DPs? Okay, that helps, thank you. Okay, so let me give a couple sort of canonical examples that I'll use for the lecture. So example one, I'll work through Acrobat balancing with noisy encoders. Okay, so instead of having full state perfect observations of X, the positions and velocities of both joints, let's say I've just got a joint sensor that tells me the position instantaneously, and it's even a little noisy. So how do we design a controller for that? Right, first of all, the plant, when you go to model this thing, and you could be doing this in your project if you wanted, right? So we've already got Acrobat plant living around, but in the block diagram view of the world, we also have a bunch of sensor models. So for instance, we have a rotary encoder model lying around. So I've got the full state of the Acrobat plant coming out, the rotary encoder knocking that down into Q, which would just be the joint positions. Potentially perfect. Actually, the rotary encoder class in Drake actually does quantization and stuff too if you want to model some of the more detailed elements of encoders. Okay, and then we can add in some disturbance, right? This would be now an observation noise, so I'll call it V. And this is the signal that's going to come out, okay? I've got my U going into the Acrobat. I can add process noise W into the Acrobat 2. So the system that we want to control now is actually the system that is the combination of all those different things, which has noise, random inputs, but the input of interest is U, okay, and the output is Y, and I'm into this sort of, that's my plant. And my goal is to design a controller that will somehow take the Y's and map it back to the U, and that controller is going to have to be dynamic now. Because a single instance of the position, you have no idea what the velocity is. You can't do optimal decisions just from a single snapshot, especially a noisy snapshot of positions. So of course we have, when we do real acrobats in lab, we have that going on. And when you look at the subtleties of balancing, for instance, a lot of the pain is actually from the estimation that has to go on and overcome some of the sensing limitations, but also stiction limitations and other things. That's what causes these imperfections actually in the acrobat balancing. We saw it also when we talked about quadrotors stabilizing in wind, right? We had to actually had to build a dynamic controller for that. I kind of glossed over it because we hadn't talked about output feedback yet. But remember that the plant that we're stabilizing in that case was the state of the wind plus the state of the quadrotor. Clearly, you don't have direct observations of the state of the wind, so you have to do some sort of online observer-based control in order to estimate the state of the wind and make these control decisions. Okay. We'll build up that, but just to contrast that as a second example, imagine I've got a manipulation example here. Okay, so I have let's say a UR3 robot with some objects in the scene. Is my nominal plant. That's maybe my multi-body plant in simulation, which has to go to a scene graph. Okay, and this actually goes to an RGBD sensor model. And let's say that my output Y is actually a camera image, maybe a depth camera image. Okay, and I have actually, when you really go to model more complicated robots like that, you also have a low-level controller here, and maybe the actions that I want to send in are actually abstracted a little bit away from the torques on the robot. Okay, so similarly, I could imagine trying to design a control system for that input-output system. Like something like this. I'm got a robot trying to pick up and just reorient a mug, right? The difference actually is, in some sense, small. But there's the big defining difference between these two examples is that this one has a camera in the loop, okay? And that camera, as of today, I hope the story is different a year from now. As of today, the existence of this camera inside my system makes me take almost an entirely different set of tools to try to solve this problem versus this problem. Okay, but one of your jobs as future roboticists is to fix that, because I feel like that is just, we're maybe throwing the baby out with the bathwater, right? So we know lots about how to control this part. Someone just throws one little sensor in that's kind of an ugly sensor that's discontinuous and changes with lighting conditions in bad ways and whatever, and it's high dimensional, but that really shouldn't break everything. Okay, I'll get back to that towards the end. But the approaches, I'll talk a little bit about the approaches we used for that kind of system too, right? And these tend to be much more learning-based approaches. And I think one of the most exciting things and important things that's happened to control in the last few years has been the ability to handle cameras as a sensor, right? The fact that we have deep learning perception working well enough and more detailed interactions between raw pixel feedback directly into making controllers. And when you hear papers, read papers about sort of that kind of feedback, they might sound very disconnected from here. The way that you get the controllers is actually very disconnected, but they all fit directly into that list, right? They all have an interpretation as either using a short history of observations, using a latent state, something like that. Okay, so I would like you to end this lecture with a kind of a slightly unified view of all the model-based things we've been talking about and the learning-based things, and maybe a path forward about how we can bring them together. There's actually the reason I picked these couple examples here of visual output feedback control is that they are very much a rigid robot interacting with a rigid object. The state of these objects is easily represented as a position and orientation of the T, for instance, in this case. We know a little bit about how to do contact dynamics, right? Really, everything in the diagram is stuff we've talked about so far, except the camera. The camera today changes everything, okay? All right, so that's the plan for today now, is to just dig into a few of these different cases, give you a few instances of how people are thinking about them in the world, right? And try to make some connections up and down. Questions at that level? All right. That one at the top, that static output feedback, it's so tempting. It would be so nice. Wouldn't it be so nice if you could just learn a simple function from y to x? Of course, when y equals x, that's fine. That's enough. When y is just the positions of my acrobat, it's kind of clearly not enough. Okay, but you could still ask, do we know how, for systems where we have equations that we like, let's say they're polynomial or something, okay? Equations that we like, do we know how to search the space of functions that are output feedback, static output feedback functions? Do we have good optimization recipes for that? Right? You could still say, I'd want the best, even if if it's not sufficient to solve the task, I could still say, can I just find the best controller in the family of static output feedback? Okay? Turns out even that is hard. NP hard. There's clear hardness results. Okay, so actually I can just put it on the slide. This is simple enough. Right, so this is, remember when we talked about policy gradient, we talked about for linear systems, there were well-known results where we could say even though searching directly in K it was not a convex optimization problem, but it had no local minima. And I said there's some counterexamples. You don't have to go very far to have a counterexample. Static output feedback is the first source of counterexamples. Okay? So if I have x dot equals ax plus bu, y equals cx, the simplest one that I've seen, I was asking Sasha Magretsky, my friend Sasha, I was like, what's the simplest example you could come up with for why static output feedback is bad? And he came up with this. I don't know, it seems unlikely that if Sasha, even in a hallway conversation, came up with this one, it's probably pretty minimal. Like it probably couldn't do it in 2D or something, in two states. Okay, so very simple A matrix, very simple B matrix. C is just a single row, which means I have a single control action, a single output, which means my controller is a scalar, u equals negative ky. Okay, that's the linear static output feedback. I could parameterize richer static output feedback, but if I just want to search over the class of linear static output feedback, then I just have a scalar to parameterize. Okay, so what this plot is saying that if I write the closed loop performance of using a particular k, and I plotted the eigenvalue, the largest eigenvalue of the closed loop system. But basically, if the largest eigenvalue is greater than 0 in a continuous time system, it's unstable. Okay, so the point is, just in this super simple system, only one parameter that I have to design. As I move that parameter along, it's unstable, I'm getting to something good. Maybe the optima is right here, okay? But if I started over here, the only way to get to the optimum is to go through unstable controllers on the way back to stable controllers. So at least the way we've parameterized it here, with a direct search over k, you have to go from finite cost to infinite cost to finite cost again in order to get to a good controller. Okay, so static output feedback is full of these sort of examples which shows that it's an ugly, potentially ugly cost landscape. Yeah?
So is this telling us like what a root locus plot tells us when we see when it crosses the,
Yep.
the y-axis?
This is not quite the root locus, but it's certainly related to that. So I'm plotting only the real value of the eigenvalues. So this would be, anything that's above this line would be to the right half plane of a root locus. Yeah, good. Yeah, so anything here is unstable. Maybe that's interesting. I could have plotted it in that way. Maybe that would be visually helpful for those people that know that. Okay, the point is output feedback has hardness results. And so there's a famous result by Vincent Blondel when he was here visiting at LIDS, and he wrote a paper, static output feedback is NP hard, which is unfortunate because then everybody stopped working on it because it's hard. I'm not going to be able to solve that problem completely. And I think that actually had kind of a bad effect on, or maybe the field kind of walked away from that a little bit, even though, so when someone says, oh, I've got a problem and it's NP hard, I'll be like, okay, that's fine, but I'm not stopping because of that, right? Because actually, if the instances that I care about, it doesn't mean that every instance is hard. It means that there are instances in the class of problems that are hard, right? But if the world coughs up problems that don't happen to be the ones that are extremely bad, then I would still be okay, right? So I think it's a slightly conservative view of the algorithmic challenge of the problem. Okay, so sadly, because of that, there's not a lot of great tools. I mean, I could show you, or you could figure out from what we've done how to use like sums of squares alternations, for instance, to do static output feedback design. Okay, but there's no guarantees that it's going to converge. We know that the problem space is ugly and bad. Okay, so it's possible, but it's not great, that first one. There be dragons there. Observer-based feedback is super common. And we could spend, you could take an entire semester thinking about state estimation kind of problems, but I can get at it pretty quick. So the standard form would be to say that if I have my original dynamics, xn plus 1 is f of xu. I'm going to evolve my state according to let's say I have a current state estimate, x hat n. Okay, I take a control action u. The real system is going to be perturbed by some noise, but I'll just pretend the noise is 0. I'll be an optimist, okay? And I'll evolve my dynamics like this. But I'll add in some observer dynamics, okay, where I say I'll take the measurement that I'm actually getting and compare that with the measurement that I expected to get, again, with some optimism about saying that there was no measurement noise. Okay, so this L is called an observer gain. And it's just a way to do some simple feedback to try to drag my state estimate towards predicting the observations that I'm actually seeing. And this is a very common standard form. This would be called the Leuenberger observer form. But for instance, if you know like the Kalman filter fits in this form where L is just the Kalman gain, a particular choice of this matrix L. But the more general class, if you were to just pick L by hand, for instance, you'd call it a Leuenberger observer. And if you found the optimal L, you might call it a Kalman filter. Okay, so that's an important class of very simple dynamical systems. And then if I proceeded to say, for instance, that U of n is now pi of x hat of n, can you see why I'm calling that a control system, a dynamic control system, right? Where x hat now is the internal state of that control system. This is the dynamics by which it evolves, right? Which is a function of the inputs. And then I have an output function like this. So it just kind of flipped. F is still used in the internal thing, but now pi is my output. Okay, and there's all kinds of things we can say about this. Like in the particular case of F being a linear system, we can look at the matrix, just like we talked about A minus BK as the matrix of the closed loop performance. If I had an A and a B here, then A plus LC becomes the matrix that determines the stability properties of the observer. It's very, very analogous, okay? All these things sort of have a dual in the observer space to what we do in the feedback space. Typically, or oftentimes, L is designed to try to be the optimal observer that tries to converge in some least squares sense optimally, and that would be the Kalman gain. And if you haven't seen it, the Kalman filter, the way you solve for that Kalman filter gain, the same, just like L is kind of the dual to K, the feedback, turns out the way you'd find L, maybe unsurprisingly, is you solve an almost identical Riccati equation to the way we would solve the LQR controller, right? So all of the observer design is almost exactly dual to the feedback control design. There's infinite horizon steady state Kalman filters. There's the finite horizon Kalman filters, right? If you don't, it's all the things we know about LQR, you can do exactly the same things in state estimation. So one of the most famous results, which I won't belabor, but one of the most famous results in output feedback design is that LQG design, linear quadratic Gaussian systems, the optimal output feedback controller is just the Kalman filter plus the LQR. Okay, I'll say that again slowly here, but the linear quadratic Gaussian problem right, if I have xn plus 1, axn plus bu, n plus, I could even put a covariance here, but let's just keep it simple, plus wn, yn is cxn plus d un plus v. If these are white noise, so IID mean zero Gaussians, then you can go through the exact same Riccati equations. You can design the cost to go, which is the expected value of, for instance, the infinite horizon. I did discrete time, so I'll do discrete time here. X transpose QX plus U transpose RU. And the optimal controller, this is one case of output feedback where we do have we can solve optimally. The optimal controller is the Kalman filter plus the LQR controller. So this becomes u, this is my x hat, and this is my y's coming in. You could argue that u should come in too, but. Okay, so this is the extension of LQR into the output feedback space. And in this particular setting, we have a beautiful closed form solution. And in this particular setting, that observer-based feedback is actually optimal, where it's sufficient to make control decisions down here based on only the estimated state. This fact that particularly in LQG, the control problem sort of separates into an observer design and the feedback design, which can be solved independently. This is famously known as the separation principle. The fact that you can decompose observer design from LQR design. And I think many of us have said that this is sort of the best and worst thing that has ever happened to control, right? It's the best thing because for linear Gaussian, it's amazing. You can just completely separate the problem. It's the worst thing because everybody continues to apply this, even when it's not valid outside of linear Gaussian quadratic regulators. Right? It's very tempting to say, I've got a nonlinear system. I'll use a nonlinear observer. I'll just estimate the state, and I'll write a state feedback controller and put it through here. But in general, that's not true. Have people seen LQG before? Have people seen Kalman filters before? Okay. Yeah, it's an amazing, so you've seen, the result follows naturally from when we spent the time talking about why LQR, if you have a expected LQR with Gaussian noise, how it's still the original LQR. We kind of went through that math. The best thing you could do in a Kalman filter, you could imagine, for instance, that the thing you would have to pass through here would be a complete belief state. That would be the most information you could possibly send through, right? Would be to say not only x hat, but since a linear Gaussian system will always be linear and Gaussian, you could imagine that I could perfectly represent the belief distribution of the linear system by estimating its mean and its covariance. Okay? So that would be, we know that that must be optimal because that's a complete representation of the history of observations and actions. Okay, and it just happens that because LQR doesn't depend on the covariance, the control gains only depend on the mean, which is the result we already saw. That's what gives us this separation. Okay? So let's put that to work. So I can take my acrobat example, and I could take my outputs Y, which are my noisy encoders. I can build a Kalman filter with a call that's almost, it's just as simple as calling an LQR controller. I'll take my Kalman filter. Then I'll hand that to my LQR controller. And I'll send it back all the way around to U, okay? Do that here. Okay. What's interesting is, this is just an acrobat swinging up and balancing. It is different than the original acrobat swinging up and balancing. I only did it once. I didn't hit reset here, but the convergence of that towards the equilibrium is different than the original one. How is it different? The LQR gains are the same. That didn't change. Would expect it to be, let's say, a faster or slower convergence to the fixed point? Slower, right? It takes time for the state estimate to converge on the optimal, right? What's the state space of this dynamical system? If I were to just take that whole diagram now and say, how many states does it have?
6.
X is 4. The Acrobat has 2 positions, 2 velocities. And the state estimate is also 4-dimensional. So there's a total of 8. Okay, so something that's perfectly reasonable, I think I even have it lower in the notebook, okay? You could, if you wanted to verify the stability of this system, this closed loop system, then you should actually be looking for a Lyapunov function that is in 8 variables, right? And you can find a Lyapunov function that's a function of both x and x hat and show that that combined observer plus plant plus control all converges to the fixed point. Okay, and you'll find that the rate of that is going to be slower. The state estimator is only going to add lags, right? Yeah?
What are you measuring here?
This was just the rotary encoders, so I'm basically giving it position measurements, even noisy position measurements, and not giving it velocity, instantaneous velocity measurements.
How coarse is the encoder in this example?
Yep, I think this one yeah, let's say it's continuous, but you can add quantization effects. Yeah. I don't actually remember I can check. Yeah, I think I just let it be a perfect encoder. But the class supports both. Yeah. I wonder if we could, well, if it was in Python, I would just change it. Yeah. Yes?
So when we do this kind of like convergence analysis of our state estimator,
Yeah.
Is it not sufficient to do kind of this like separation of the optimal functions to analyze the stability of our state estimator and then the stability of our controller given some kind of state, or are they inherently linked?
So what could go wrong? So the question is, so could I separate the Lyapunov analysis of this full state controller, for instance, from the Lyapunov analysis of the, so let's say that my state estimator is very slow, right? And as I'm trying to converge, somehow, let me think of a good example, but you could imagine just sort of like completely leaving the region of attraction while you're waiting for your state estimator to converge. I think they are hopelessly linked, right? In some problems, the state estimate can be fast relative to the time constant of your dynamics, right? So if you have like a wicked high rate IMU, low noise, whatever, then you can hope that the convergence of your state estimate is just so fast relative to the convergence of relative to the time constants of the dynamics that you could effectively separate them. But if you have measurements that are on the same sort of time constant as your dynamics, then they are hopelessly intertwined. Yeah?
Earlier in the class, you mentioned like contraction for composing
Yeah.
nonlinear blocks. Can you do that in this case?
Yeah, that's a great question. So since I have 2 dynamical systems that each have their own state, and we talked about possibly the composition or small gain theorem, kind of, there are a handful of ideas that have come up through the semester of the ways you could compose contracts. If you had L2 gain sort of bounds here and L2 gain bounds there, then you could potentially compose them. You're right, contraction analysis is another way that sometimes has these rules of composition, that you have a contraction metric for one, a contraction metric for the other. You could ask if you have a contraction metric for the full thing. Absolutely. Yeah. You could even say that, like, you could try to break up the Acrobat plant, right? It's just, the question is just how coupled they are and how, yeah. Yeah, so the more detailed model of the Acrobat, if you actually want the real, sim to real, and you want to see this kind of like oscillation and everything like that, there's a bunch of things. We actually spent some time at one point just saying, like, can we reproduce that annoying phenomenon we're seeing on the real hardware in simulation, right? And so we just made our list. We said there's quantization error, there's backlash in the actuator, there's stiction in the actuator, okay? The particular hardware I showed was actually designed to be as low stiction, as low backlash, as low, it's a particular transmission Zach, who's a great mechanical designer, built. It's meant to have no backlash, I guess. Yeah. Yeah. So, but it still has this, right? This sort of phenomenon. So I think stiction is the biggest problem that we identified at the time. And if you ask what is a control theory response to stiction, you very quickly get into hybrid systems, right? You actually have to think about being in different modes. When you're in stiction mode, you're sliding mode. You can't have a simple static feedback that ignores that hybrid nature. You won't get smooth sort of controllers that sort of magically resolve stiction. Okay, but all the tools of the class can be brought to bear on that. Okay, so this is a really big deal. Like the fact that, some people will like get to the output feedback lecture in their controls class, and this would be the only thing they would say, right? This is like output feedback in the eyes of linear control. Okay, but I want to think of that as a bigger picture, right? This is sort of one view of control, is that I've got an observer and then a full state feedback controller. But I want you to lift that view and think about this not as, observer plus state feedback controller, but really what we have is this dynamic controller, right? Which is taking in measurements y and outputting u, with the internal state as my x hat, right? So you could completely write the controllers like this in a more general form. We put these subscript C here to identify them, distinguish them from the ones that might be in the plant. Okay, so is that clear? So this is the model of the plant. But the system we just built, that's the optimal controller, can also be written as a linear state space dynamical system, right? The AC here is actually A minus LC, or A plus LC, right? But otherwise, it's exactly the same. In fact, you don't even need these to describe that particular dynamics. The controller is deterministic. Good. Yeah. So U and Y over here. Yeah. Good. Okay. So natural choice. So remember we talked about LQR. We could solve it with the Riccati equation. We had our special solution. We also had different ways to search directly over K. We had policy gradient approaches. We even had a linear matrix inequality, a way to search over K directly. So the generalization of that type of thinking, and really I think the powerful way to think about output feedback, is to say, could I do a more direct search over these matrices to try to find the best controller? Okay? And the answer is yes. You can search over the class of dynamic linear controllers for linear systems that have not, so it's, when you have an LQR objective, then you would just solve the Riccati equations. You might as well. You're not going to do better. But if you had like a robust design problem, or once you switch to the optimization view of this, then you can combine objectives. You have a richer specification. So the generalization of this is trying to search over these matrices to try to find the controller. And there are a couple important results in that world. There is an LMI approach. You can solve these with convex optimization. Via a change of coordinates. Change of variables, if you will, due to Scherer. So the same way, remember I said that the reason some people weren't surprised that LQR gradient descent worked for LQR is because they already knew that there was a change of variables that made the problem convex. Okay? So we actually, in my lab, we lost a bunch of time saying, well, wait, if we know there's a change of variables that makes this problem convex, does that also imply that you could do gradient descent on these parameters and it would work? The answer is, not quite, almost, like so close. And we understand so much more about the problem than I ever thought I would, okay? But that's a little bit more nuanced of a problem, which is really interesting because people use reinforcement learning, which is a gradient-based search, to search for output feedback fallacies. And even in the sense of a linear system, we know that it doesn't always work. Okay? Well, that's a little, actually, it's more subtle than that. I tried to sort of summarize it on a single slide here, this world of results. Okay? I think the state of the art today, unless something came out last week or something, right, is of what we understand about gradient descent in the optimization landscape of LQG, is we know that there exist we know there exist saddle points, places where the gradient goes to 0, which are not optimal. The current best understanding is that they tend to look like this. So there's a chance that gradient descent will always work as long as you have some momentum. Okay? But we know it is not the case that that all minima or all stationary points are global minima. That one is lost. But there's a chance that gradient descent could still continue to work with momentum. Okay. But this is like at the forefront of what people are doing, trying to understand optimization landscapes for RL, for instance, right? If we don't understand the linear system case, then we're not going to understand the full case. And this is, I think, a very fruitful line of work. Yeah.
It's not immediately obvious to me how we get the coefficients for the dynamics of our controller, like the AC, BC, CC. Where are we? Are we just initializing those to some value and then trying to figure out what they actually are, or is there some more derivative?
In this setting, yeah, so this one we could do direct search. Let's see. So the claim in that approach of trying to do gradient descent would be you have to find an initial stabilizing controller. Otherwise, you're in the infinite cost regime and gradients aren't good. Okay, find an initial stabilizing controller by whatever means necessary. You could use other approximations. And then start doing gradient descent directly on the parameters, the values of those matrices. Yeah. And what we're saying is that if you do that, you might get into a place where the gradient goes to 0, but you're not at the optimum. But try to keep going. It's interesting to think. So for instance, if I said I can solve this by searching over AC, BC, CC, and DC with convex optimization, just with a change of variables, doesn't that seem inconsistent with the fact that I said output feedback is NP hard? Because certainly AC equals 0, there's an output feedback version of this inside there. Okay, a static output feedback version of it inside there. All right, so there's a caveat to this. This works when XC is greater than or equal to the dimension of the original plant. So it has to be that it could be a full state observer in order for this to work. So technically, the optimization landscape, for the arbitrary ABC matrices, has a non-convex rank condition, which when XC has the dimension of X, that rank condition is trivially satisfied and disappears from the optimization problem, as long as XC is the dimension of X or bigger. Okay, so there's no, everything is consistent and beautifully and understood in these realm. So let's generalize this. So what's the natural, so now I've got neural network power. In 2023, I would just say this is not the class I really care about optimizing over. Let's make that a recurrent network, for instance, right? And let's make it maybe the output of that. So an LSTM, or any general recurrent network, is basically a state space form of these equations. Right? So you could imagine directly going and searching over the parameters of a neural network as being a very similar optimization problem. There are other ways that people are currently representing these systems. So you know that even for linear systems, state space representations aren't the only representation of choice. That board's pretty messy. I'll go up here. That's a pretty common way to represent state space, or to represent a linear dynamical system. But you can also do autoregressive models, right, for linear systems. So for instance, you could write U of n is some combination, linear combination of old u's plus some linear combination minus I. I guess probably I could have used A and B for the opposite, but I could write the output of a linear dynamical system in a form like this, and there's a one-to-one mapping. If I make those vectors and everything like this, I could take any state space equation and write it as an autoregressive form. I could take any autoregressive form, write it as a state space equation. Okay. So this is just saying that given my current, it's a little confusing. I don't like, in my eyes, to see that with U being the output and Y being the input, but it's because I'm doing the controller, right? But I guess, so I think that's fairly consistent for this lecture, but it drives me crazy looking at that. Okay. I can just understand that I can write the same dynamical system as a function of the history of observations. That might be a infinite history. Oftentimes, a finite history is sufficient. Yeah. So when you think about these class of models, and you want to think about the neural network generalization, these would go to the recurrent networks. And this class of model would generalize to, these are called ARX models, autoregressive with X stands for with exogenous input, which is just kind of silly. But what does this go to? What's the neural network equivalent of sort of that kind of model? Certainly, you could just do a feed-forward network that takes a history of observations and maps it to the next one. But this is a transformer, right? Right, so transformers looked weird when they first came on the scene, but they're really just kind of the obvious sort of state space, or the ARX version of a dynamical system, and recurrent networks are just the state space version. And then when people talk about, ChatGPT has a finite memory in some sense, right? And they're saying, well, maybe we need to put recurrence back in. That all makes sense if you think about it from the dynamical systems point of view. Right? This can output have an infinitely long impulse response. A transformer can. But there's a few games you can play with ChatGPT that it can't answer. Like you could say, give me 40,001 unique random variables, something like that. Like it can't answer that question because it's got a history of 40,000 or something. But if you said, tell me a story that's longer than 40,000, it would be able to do that because it's autoregressive. Okay, so people are searching now over these rich classes of parameterizations, and the game becomes how do you design, how do you search in that space effectively? In particular, these things pay off when you've got cameras in there because you need the representational power of a neural network to go from the RGB image down into a control game. Okay, but really the exact same story we've been talking about this whole time works. It's just a matter of how do you do that search. And what people are mostly doing is these gradient-based searches in those high parameter spaces. I would say there's two things they're doing. So let's just talk for a minute about what I think is sort of the best thing that's happened in controls in the last few years is when people started using cameras in here, right? So people were doing it, so like at Berkeley, they were doing it for a handful of years. I was a little skeptical, honestly. I didn't completely believe. This was the project at MIT. You can tell by the MIT hat with Pete Florence and Lucas Manueli, and they just solidly convinced me that they started building. They used imitation learning in this case to design visual motor policies. And this thing was just rock solid. You could go in, you could do anything you wanted to perturb the scene, and this thing would always accomplish non-trivial tasks, hanging a deformable hat on a rack, picking up plates, which was one of the hard cases we had in our in some of our model-based control, flipping up shoes and sugar boxes and stuff like that. Okay, so originally, before we got into transformers and bigger models, the visual motor policies looked like this, right? They looked like a relatively simple controller. They looked like a mapping, an encoder that took an observation or a small history of observations down into a latent vector, Z. And then we tried to fix a static policy from that latent vector Z into the actions. Okay, and that was already working incredibly well, right? So this was just one of the ones that, you know, I think you can see the videos, and that's what I did. I saw the videos for a while. I was like, that looks pretty darn good, but I don't really know. You know, you can make videos look good. And then when it started happening in lab and you could really go in and knock the plate around, I was completely convinced. If you knock the camera around, it completely fails. But the scene, the visual scene can be changed pretty dramatically. Right, this was for me like, wow, you know, we've been saying it's important to close feedback loops around cameras, but this was just like, now we just can't do anything else. We must close feedback loops around cameras. So the question then becomes, how do you come up with those gains? There's really only a handful of ways that people do it. And this is where I say that people throw the baby out with the bathwater a little bit, right? In most cases, people say once you're doing this, you have to use RL or you have to do imitation learning, okay? The RL case, even then, oftentimes you fix, not always, but oftentimes you certainly pre-train your big neural network. So think about that neural network going from RGB down into whatever. That's like a ResNet or something big, UNet these days maybe, okay? And that's pre-trained on a lot of visual data because RL doesn't want to go through a million parameters, all right? You can either fix that or allow it to fine-tune that, and then you start doing gradient-based optimization, mostly on these parameters. And in RL, these parameters are actually pretty small. These tend to be a very small neural network. The other way people have been doing it, which is, I think, been highly successful, is with imitation learning, right? So RL was the first way, but I like to point out this, you know, this article by the head of Google DeepMind research that just talks about how much people started shifting from RL to make a manipulation demo work, for instance, to behavior cloning, which is the simplest version of imitation learning. There's kind of two branches of imitation learning. One would be inverse reinforcement learning, where you watch imitations and you try to infer the cost function and then solve an optimal control problem. The other one is behavior cloning, where you just try to copy. You get examples of observations and actions that were taken by an actor, and you just use supervised learning to try to bring that in and copy it. And that is just working so well, right? That's what we did here. We used a particular type of perception system that was using dense descriptors to try to extract the RGB images down into something small and consumable by the policy, and that worked really, really well. But this is what we're doing these days at TRI, that the best manipulation demos that we can put on are, I would say, surprisingly good. I kind of, even just this morning, you know how I joke, I have like 4 examples that I always use when I talk about state representations and like, I talk about buttoning my shirt, I talk about tying shoelaces, I talk about spreading peanut butter on toast. And damn it if they didn't just spread peanut butter on toast this morning, and they're like, we're doing the buttons tomorrow, and I said, if you tie your shoelaces on, I'm gonna retire, right? But the way they're doing that is they're just doing human teleop through the robot to give enough demonstrations, and then they're copying that into the weights of a big neural network, a particular style of big neural network, and they're getting visual motor policies out that are just incredibly good. All right, so the one that's working best for us today, oh yeah, please.
Just to go back, are the policies learned for a particular action or a particular, like, I don't even know how to describe it, or are they?
We use the word skill.
Okay.
Yeah, so somehow there's some, and what's a skill? Don't ask me to define that. No, everybody's got their own definition. People say like something you can do in 3 seconds, or something a human could do in 3 seconds, or whatever.
Generalize? Can you build a controller around it where you say now do this, now do that, and it'll?
This is one of the biggest questions in the field today. So some people think maybe imitation learning will go the whole distance. Okay, what would that look like in control? So what if we had a foundation model for control? So maybe if I train with just imitation learning enough different skills, then somehow I get zero-shot generalization, and I could do a new skill that I've never done before just by having learned enough different skills. Everybody's in that race right now, right? Right now they're narrow. Right now you train at around 100 demonstrations of a particular skill, like rolling the dough or something like that. And within the sort of convex hull of demonstrations you gave it, you'd expect, which is poorly defined, but if you somehow, we've plotted the various feature vectors and said, like, if we're roughly near the demonstrations, then we expect it to work very well, even for very dexterous tasks. The particular way that we're doing these diffusion things right now is with these diffusion models. How many people know diffusion models from generative models? Yeah? Yeah, so it's one of the ways that it was popularized first for image generation, right? So DALL-E and stable diffusion. Stable diffusion was I guess the big one. The idea is very, very simple. Okay, if you have an image and you want a bunch of images, you want to generate more random images, then take your image, and it's easy to add noise to the image. Take your image and just add noise and noise and noise until the point it becomes just random pixels. And what you do is, as you add that noise, you learn a model that goes backwards. You've made training data that goes now from noise to a beautiful image. And that's the diffusion. This way is adding randomness is the diffusion, and then going backwards is the thing that generates new images. So you just start with a random vector, and it becomes beautiful images. And in the control case, it looks like this, right? So you go from a random possible control actions, and then it diffuses into becoming trajectories of actions for the robot. Okay. The reasons that this is the best today for us are very subtle. It's about what trains very robustly, right? It's about the amount of hyperparameter tuning. It does solve a very core problem in multimodal demonstrations. We were struggling with that for a long time, that you'd have a human that's giving demonstrations of a task, and they would sometimes, like in the T task, they would sometimes go left around the T, sometimes they would go right around the T, okay? And the diffusion model is strong enough to learn the distribution of possible actions, whereas some of the other approaches were not doing that very well. Okay, but if you ask like what's working best in output feedback control today, for a narrow demonstration, I would say this. It's just really robust. Every new task, like I said, spreading peanut butter today, It's really, really powerful things. The question is, I mean, the big question is, does imitation learning scale? Is that enough? Do we just have to put humans to work, demonstrating enough things, or come up with a business model, or gamify it, right? So everybody's playing Pokemon Go, but they're actually training robots in the cloud. Something like that could just bust it open, and then we have our GPT moment for manipulation, for control more generally. I don't know. Other people are betting on model-based control, for instance. Maybe you have planners that you can generate random environments, random tasks, solve a really good planning problem, and then generate enough training data that way. That would reduce the burden on human demonstrators. Of course, those could work together, right? This particular one stood out as a challenge because the first, this was a project that was started as an intern project at TRI. Chung, who did this early in the summer, he came up to me and he said, so can you just give me a planner that solves the optimal path for this? And I was like, no, I can't give you a planner that just reliably, rock solid, reliably does that. You guys are all in the middle of projects that are struggling with planning through contact and stuff like that. I can give you one that'll work sometimes, but not all the time. But let's see. Now we can do it. This is last week. We now have graphs of convex sets planning globally optimal paths with convex optimization for the T. So that's progress, right? I don't know. I'm very optimistic about how far it will go, but we'll see if it goes the distance, if it beats human demonstrations. But this stuff really just works. You could almost if you were to visit TRI these days and you had 3 hours, we would you'd say, come up with a task, learn how to teleop the robot in the first 10 minutes, and then come up with some task that we've never tried before and train a robot. It's a little bit unsatisfying in the sense that you do the training for 3 hours and then it has to train over, the diffusion policy trains overnight on the cloud. The next day you can test your policy, but that'll come down, right? This is another example that I would just really like. What is the state of the sauce, right, or the pizza or whatever? I don't know how to do a model-based control for that. In fact, that project was explicitly designed to be the things I don't know how to do simulation for and control for. Yeah.
So in this example, if you say if you try a new sauce that's thinner or pizza crust that's heavier, or
Yeah.
a handle that's heavier, does it still work?
So I think the convex hull of the demonstrations is kind of the right. That's too vague, but it's kind of the right. It's a pretty operationally useful understanding. So if you had a different crust, if you give it enough crusts that are softer, harder, whatever, then I bet it would generalize in between. It doesn't extrapolate very well, but it does generalize very well. Yeah. Yeah.
If you do something like that, is it going to come up with a policy that works the least poorly for everything, or is it going to come up with a feedback where it kind of infers the quality of the sauce as it goes?
So these are big models. They are taking history of observations, predicting the next handful of actions forward. Somewhere in those weights, you could argue that it's doing prediction. It's got some I think the right way to think about it is it's doing an approximate belief state somewhere in the middle that is taking the history of observations, compressing that into a useful representation for control. I just don't think that that's the only final. I don't think imitation learning is the final answer. I think I tried to put that acrobat and the robot right next to each other because the only thing that changed in some of these problems is we put a camera in there, and that just shouldn't break everything. Yeah.
If you can do pose estimation on a video, can you use a video as the thing which you're imitating on?
That's another. So I would say there's a handful of bets. One is just scale up imitation learning. A second one, which you're alluding to, is watch YouTube, right? That's what you do. Okay. Yeah, I mean, it's interesting to think if you're actually learning new dexterous skill. I mean, certainly, like I learned how to fix my bike crank or something like that. Yeah, no, like I think that could be a source. And the big question there is, do you need to? You're only getting observations of the. You're getting the Y's. You're not getting the U's. Can you infer what the U's? Could you get a little bit of data to infer what the U's are, for instance, to then label all the Y's and then train like that? This is one of the big questions. Yeah, and then I think trying to do generative models and maybe state feedback design with RL, with planning, whatever, and trying to map that into output feedback, I would say would be one of the third big bets. But everybody's waiting for the foundation model moment for control, and I would say it's coming. I would say there's problems that fit into the frameworks we've talked about all class that would be, I think, I would not expect a model to be able to memorize, but I think most of the problems we've talked about are actually sort of small enough compared to like the English language, right? I mean, I think you could just memorize most of the control systems that we've talked about. So that's an approach. We do have, I mean, I'm out of time. We do have ways we can do sums of squares optimizations on pixel-based feedback. All these things are progressing, right? But hopefully that gives you kind of a taste of output feedback. All right, one lecture left for me, and then next week is projects. We'll send out more details on project, everything on Piazza. And I know some of you ask questions, and many of you are asking questions, but don't silently struggle. See you Thursday.